So along with the cathode ray tube experiment and also Millikan's oil drop experiment, which helped to characterize the negatively charged particle in the atom, the electron, it was known then that there had to be something positively charged. And so this is where J.J. Thomson proposed his plum pudding model, where the atom was still thought of as being a spherical object, and somewhat of a solid spherical object, kind of like a billiard ball, except now, instead of just being a plain billiard ball, it was like this plum pudding idea where the plums in the pudding would have been the electrons. So it would be like a polka dotted billiard ball, if you want to think of it that way. And so that was the prevailing theory in the early 20th century. And as scientists do, they continue to test and run experiments and gather new evidence and see if that evidence supports the prevailing theory. And when it doesn't, just like when Thomson identified the fact that these cathode rays were the same no matter what element was being used for the electrodes, he knew that that current model didn't jive with the results that he was seeing. So he had to revise the model, and that's when he came up with the plum pudding model. Well, Rutherford did the same sort of thing. He designed an experiment known as the gold foil experiment. This is one of the really important experiments in the history of atomic theory. There were four main parts to the gold foil experiment. The first part was this source of alpha radiation. Now, radioactivity had been discovered by Henri Becquerel in the 1800s, named radioactivity by Madame Curie, and basically it's the result of unstable nuclei that spontaneously decay. And when they do so, they give up either high energy particles or just high energy electromagnetic photons. And so in this case, Rutherford was using alpha particles. Now, an alpha particle is essentially a helium nucleus. It's 2 protons, 2 neutrons, no electrons, so it has a positive charge. So these positively charged particles, he chose something that's going to emit those. And when something radioactively decays, it just spews particles and energy, photons in every direction. It's not, one set direction. But that's what Rutherford wanted. So in order to achieve that, he encased the alpha source in a lead box that was only open on one side, and thereby only the particles that decayed in that direction would be able to escape. So in effect, he created a beam of alpha particles, and that's the second important part of the experiment to be familiar with. So that's his stream of projectiles, and he directed it towards his target, which was a sheet of gold foil. And at first blush, you might look at that and think, well, why in the world would you choose gold? I mean, in a world where you want to try and minimize costs, why gold? Because gold's not cheap. The reason he chose gold is because gold, like most metals, is very malleable, which means that it can be pounded out flat. When you hit it, it's not going to crack or deform. It just tends to flatten out. It absorbs the energy. And gold in particular is extremely malleable. So if you take a look at this image here, right here, where there's that tiny little dot, okay, that's a gold nugget. That's a gold nugget that's about 1/2 centimeter in diameter. Now, if you remember, the width of your pinky finger is about 1 centimeter. So imagine a gold nugget about half the width of your pinky finger, and you take that nugget and you flatten it out. And if you flatten it out as much as you can, you would get a sheet of gold that is this size here. Now, for perspective, that is 1/2 meter on a side, so that's about 50 centimeters. So hopefully you can see this. It's about that big on a side. Okay, so from a tiny little nugget to get something that big, obviously it's going to be very, very thin. And because that gold foil was so thin, that's why Rutherford chose to use gold for the experiment. Surrounding that target was a screen, a deflector screen, that was coated with zinc sulfide. And zinc sulfide is a material that when it is struck by an energetic particle, it's going to emit a little flash of light. And so that's how Rutherford was planning on observing what happened when a particle encountered the gold foil on an atomic level. Now, going with the plum pudding model, the thinking was that most of the particles were going to sail straight through. Okay, And in fact, most of them did. There were some that there was a little bit of deflection. So Rutherford was expecting these hits here and not really surprised when he saw the majority of them hitting there. Some of them made it to the backside of the gold foil. They passed through, but they were deflected at large angles. So he may have been, that might have been mildly surprising. But what really knocked his socks off was there were actually some flashes of light in front of the gold foil. They didn't even make it through the gold foil. And the only way that could happen is if those alpha particles were hitting something very sturdy, a lot of constitution, very dense, and just getting bounced right back. And these hits right here shocked Rutherford so much that he's got this famous quote. He said it was like watching these results right here were like if you took an artillery shell and fired it out of a cannon at a piece of tissue paper. So like tissue paper you'd put in a gift bag, and watching it just bounce off. Now, if you can imagine that, how absurd that must sound, that was the level of awe that he had about these results. And that totally did not mesh with Thomson's plum pudding model. So it forced Rutherford to come up with an alternate explanation about what the inside of the atom actually looks like that would be supported by the vast majority of particles passing through, but yet some of them were radically affected in terms of their trajectory. And so the first conclusion of his experiment was that most of the atom is just plain old empty space. And that was supported by the fact that the vast majority went straight through the gold foil and didn't deviate much at all, if any. The second conclusion of the gold foil experiment is that in that atom that is mostly empty space, at the center of it, there must be a very small, and he knew it had to be very small because it was only a very small proportion of the particles that were radically deflected. It had to be very dense because it withstood, the high energy alpha particles. So very small, very dense, positively charged because, again, we know what the characteristic of the electrons are. And the rest of the atom is what we were trying to determine at this point. So it's that positive charge, but instead of being diffuse, like in the plum pudding model, it's highly, highly concentrated in the center. And that center dense particle became known as the nucleus. So we've come a long way in about 120 years worth of history. Around the beginning of the 19th century, 1800s, we had Dalton's idea of the atom, which was basically like the billiard ball. It was a single spherical particle, and nothing was smaller than it. Then with Thomson's discovery of the electron and the development of the plum pudding model, we had this idea of the small negative particles, the electrons, but a large diffuse area of positive charge that took up the rest of the volume of the atom. Rutherford's model gets us closer to our modern understanding. Still not perfect, but it's a lot closer. And the idea that the positive charge is concentrated in that central region. Now, this model, I would call it the Jimmy Neutron model, but even this model does not do justice to what Rutherford was saying in his conclusions. That central core, the nucleus, when he said it was very small, this representation here is way too big. I would say maybe something 10,000 times smaller than this. Okay, it's almost mind-boggling to think how big the nucleus is in comparison to the volume of the overall atom. It's a very, very minuscule amount. But nevertheless, we get the idea that there's a positive charged particle or area in the center of the atom. The negative electrons are outside. At this point in history, the 1920s, still don't have a real good grasp on exactly where the electrons are at or how they're behaving. But that's further to come later on in the 20th century. So again, with the gold foil experiment, make sure that you are familiar with the four main parts of the gold foil experiment, the observations that he expected and the observations that he was surprised by, and also the two main conclusions of the gold foil experiment. Thanks a lot. Have a good night.